All right, welcome to another video lesson. So previously we had looked at functions to include what defines a function. We had looked at domain and range, functions as equations and as graphs. In this lesson, I want to start by looking at another type of function equation, this one called a piecewise function. And a piecewise function is a function that is defined by two or more equations. And this is over a specified domain. Two or more equations over a specified domain, which remember that is based off of our x-axis. We're looking at our input value into the machine. It's two or more over specified domain. And this is looking at our inputs, the x variable. So instead of using one rule for all the inputs, it changes behavior depending on the value of x. So I think it'd be helpful to get right into an example of a piecewise. So if we were asked to evaluate the following piecewise function at the given values. So if we had f of x, and this is how you'll typically see the piecewise function written, like f of x equals, and then it'll be one of these bracket types here, and then however many equations, usually most often 2 or 3. So if we had 8x minus 1 and 4x plus 9, and this is if x is less than 0, and this one is if x is greater than or equal to 0. So let's start here first and look at what we have. We have a function, f of x, and it's defined by both 8x minus 1 and 4x plus 9. So how do we know which one to use to input our variable? That's what the last part tells us right here. The last part in each line. That's what that tells us. It specifies for us which domain values correspond to which equation. So for all x less than 0, we're inputting into the top equation. And for all x greater than or equal to 0, we are using the bottom equation. So if we were asked to evaluate this for, let's say, f of 5, f of -2, and f of 0. So let's start f of 5. Let's evaluate that. So the 5 is our x value, like we saw with the previously. It's what we're replacing x with. X is replaced with 5. So 5 is what we're inputting into the function. But does the 5 fall under the top equation or the bottom equation? Right? Is it less than 0 or is it greater than or equal to 0? Well, obviously 5 is greater than 0. So in this case, we know that we have to use the bottom equation, and we can just ignore the top one because that doesn't apply for what we are evaluating right here, f of 5. So we have to use the bottom equation. So we have 4x plus 9. All right, and now we can go and Now we know which one we're using. Now we can do like we've been doing before. We can replace the x with 5. So f of 5 equals 4 times 5 plus 9. So we have 20 plus 9 equals 20. So f of 5 is equal to 29. And then let's do f of negative 2. Let's evaluate that. So first off, let's figure out which equation we're using, top or the bottom one. So the top one says all x less than 0. Well, negative 2 is certainly less than 0. So it looks like we will be using the top equation to input. So we'll be using the 8x minus 1. So f of negative 2 equals 8 times negative 2 minus 1, which equals 8 times negative 2, negative 16, minus 1. So we have negative 17 for that one. And finally, f of 0 looks like it can't be the top one because that has to be for x less than 0. So not including 0, but the bottom one will certainly work for us for all x greater than or equal to 0. So we'll be using the bottom one again for this one. So we have 4 times 0 plus 9. So 4 times 0, 0 plus 9 is just 9. So f of 0 equals 9. Let's try another piecewise. Let's do f of x, and it's going to be equal to, draw a bracket, of x minus 2 and negative, and then in parentheses, x minus 2. And this is if x is greater than negative 5. And this one will be if x is less than or equal to negative 5. All right, and let's evaluate, we'll just evaluate 1 for this, f of negative 8. All right, so that's based on the information we're given. Where would negative 8, where would that fit into based on the specific domain values that were given corresponding to each equation? So the top one is only for x that are greater than negative 5. So that's going to be going the wrong way for us. The bottom one says x less than or equal to negative 5. So that is going to be the one we'll have to end up using. The only one that works. So we forget about the top equation. We are only concerned with the bottom one. So f of negative 8, and we'll be using this equation. And when we input f of 8 equals, so we'll still leave the negative on the outside of our parentheses. So inside, x becomes negative 8 minus 2. So we have negative, and then in the parentheses, negative 8 minus 2 is negative 10. And here we have a negative 10, so we have a double negative, so those come together and make plus. So we'll end up with positive 10 as our final answer. So f of negative 8 is equal to 10 in this case. And let's try one more. We'll do this one with 3 equations. So this piecewise says f of x is equal to x plus 7. And that is if x is less than 3. And x if x is greater than or equal to 3 and less than or equal to 5. And then we have 9x. If x is greater than 5. All right, let's evaluate for f of 4. So it looks like we have all the bases are covered on the domains. So this top one, this is all x less than 3. Bottom one is all x greater than 5. And then the middle one has 3, 4, and 5 covered. So it looks like 4 would only fit into the middle equation for all x greater than or equal to 3 and less than or equal to 5. So 4 smack dab in the middle of this specified domain that corresponds to, in this case, simply x. So all we would have is f of 4 equals 4. So not much to that one there. All right. So that is our introduction to piecewise functions. And now we're going to switch gears and go back to discussing functions and their graphs. And it can be very useful for us to know where the graph of a function rises and where it falls. Like say we were talking like in a real world scenario, if we had a function that was showing us maybe we're a company, maybe it's showing us cost or showing us revenue or profit. So it may very well be beneficial for us to know where we're rising, where we're falling, where profits going up, going down, where costs are going up, going down. So there's a lot of real world situations where this sort of thing could be useful. So that's what we're going to look at first. So when we say that a function rises, we're just simply saying the function is said to be increasing. And then where a function falls, then it's just said to be where it is decreasing. So we'll be using increasing and decreasing for average. But that's what we're going to look at first here. So our definition tells us that f, get some spacing. So f is increasing on an interval I if if f of x1 is less than f of x2 whenever x1 is less than x2. So let's draw this out. Okay, start it down here and okay. And we'll have a point. We'll do the points in blue. We'll have our endpoints. They'll be closed circles. And then we'll have a couple points in the middle. All right, so those are our 4 points. And then the whole function, the whole line here, this is when I was talking about increasing on an interval I, by that I just mean the actual function itself here. So from one endpoint to the other is all that is saying. So if we said that this is, all right, this is going to be our x1, and then this one is our x2, and then that'll make this point f of x1 and f of x2. So now we can make a little more sense. So again, and we're saying f, which is this function here, that's graphed. F is increasing on an interval I if x1 is less than x2, which it is, x1 is less than x2, and then f of x1 is less than f of x2. F of x1 is less than f of x2. So we would say that this function is increasing. And of course, this is the kind of the mathy definition. I mean, we could visually see that, all right, well, it's our slope is we're going, the graph is going up, so I mean we can kind of, you know, self-determine that it looks like it is increasing, but that's just to be able to see exactly what they're talking about, what specifically makes it increasing. So let's look at the other side. So f is decreasing on an open interval I if f of x1 is greater than f of x2, and still x1 is less than x2. So let's write it out, be much easier to see. Okay, we'll do our endpoints again. So like the last one, this will be our x1, and this will be our x2. I'm sure you can probably gather where this one is going. So again, this is when it's talking about on the interval I, we're just talking about the function itself graphed out. So if this is our x1 and this is our x2, and then again that would make this f of x1 and this f of x2. So like the last one, we still have x1 is less than x2, but now it's reverse. Now we have to say that in order for it to be decreasing, f of x1 is greater than f of x2 on the graph. So we just flop that. Now we would say that this function is decreasing on this interval I. But again, we can visualize that too without having to go into the technical details. We can see that clearly going down. We're decreasing in value, at least say on the y-axis. But that is how we are able to tell between increasing and decreasing. And of course, there is the third option too. If we had, it'll still be on the interval I. It's still just like the other two. X1 is less than x2. But in this case, interval I, so this is our x1. This is supposed to be black. X1 and x2. And then this will be our f of x1 and f of x2. So as I'm sure you can gather with this one, again, x1 is still less than x2, but now we would say f of x1 is equal to f of x2, and if that is the case, then our function is constant. So we have increasing, decreasing, and constant that we're able to characterize based off of looking at a graph. And of course, like we'll do in this example here, it's not always like the examples we did, it's not always going to be cut and dry. You could have points where you could have a function where it's doing all three multiple times depending on the size of the function. So it's not like it's always going to be just increasing or decreasing. But we'll do a nice example here. All right, let's plot some points here. Okay, so let's do 1, 2, 3, 4, 5, 6. Maybe we'll do plot a point there, and then we'll plot one here, and then we'll plot one. And we'll plot a couple more. Try and line these up for us. Okay, these connected. All right, so we're going to have an endpoint on the left side, and then on the right side, we're going to do, that's going to be an arrow. All right, so let's take a look at this one here. So we want to determine where it is decreasing, where the function is increasing, and anywhere it is constant. All right, so we'll start with decreasing. So we're looking at, we're going to read it like we did with the domain. We're going to read it from left, go from left to right on the function, and we're going to base it off the y-axis. So it'll end up like ordered pairs. We're going to base it off of, or excuse me, the x-axis, sorry. Base it off of the x-axis. So like here we have, let's start with this point. This point is at what, 1, 1, 2, 3, 4, 5. So -5, and then we're up 3, 5, 6. So that's at so -5 based off of the x-axis. So we start there, and then where are we going? Looks like we are decreasing. The function is falling until we reach what point here? -3. All right, so we would say we are decreasing from -5, just say comma, -3. So we would write it just like that. So again, based off of the x value numbers. So decreasing from -5 to -3. And this small area here where we are increasing, all right, we're rising again. So that starts at -3, and then looks like it doesn't go for very long, just until -2. So from -3 to -2, we are increasing. And then from -2, looks like this is just a straight horizontal line, so we are constant from -2 until it's supposed to be about 1. So we are constant from -2 to 1. And then where are we going from there? From 1, we are increasing again. We have a large area where we're increasing. So that's from 1 until, where does it stop? It stops increasing at, it's supposed to be right there, 4. So from 1 to 4, the function is increasing, and then it levels off again. So from 4 until, looks like 6, from 4 to 6, the function is constant again. And then what do we have happen? We have a drop off. It starts falling, so we are decreasing once again from starting at 6 until, and we have an arrow here, so we would be going off to infinity in this case, right? Our x would just keep getting larger and larger and larger, so we're decreasing 6 until infinity by virtue of the arrow. So that's just a quick exercise in given a function that has different, not where it's doing the same thing. We can see one where it's doing several different things, picking out which sections it's decreasing, where it's constant, where it's increasing. And again, base it off of, read it left to right, and base it off of the x-axis. That's how you get your the order looks just like the ordered pairs, but it's just strictly x values. So next, let's build off of this concept of increasing and decreasing on a graph. Because we know how to determine where it is increasing and decreasing or a constant. So now the points at which a function goes from one to the other, say decrease and increasing, the points at which the function changes can be used to find the relative minimum and relative maximum. All right, relative max and relative min, and you may also sometimes see it. Some will call it local. So either or, they mean the same thing, whether you say the relative min or the local min. So these are values of the function where the behavior changes from, say, increasing, decreasing, decreasing to increasing, whatever it may be. These tell us values that give us a relative minimum and a relative maximum. So let's take a look at this. Okay, we'll just make these will be arrows. And we'll say this is, no, this is our function, some function f, and then this right here is our, call it b, and then this will be a. And then we have points. Okay, which would make this one b comma f of b. This would be a comma f of a. All right, so our definition tells us that a function value f of a is a relative maximum of f if there exists an open interval about a such that f of a is greater than f of x for all x in the open interval. And on the flip side, a function value f of b is a relative minimum of f if there exists an open interval about b such that f of b is less than f of x for all x in the open interval. So that's our technical definition. But what are we really saying here? The key word is relative or local, whichever you're using. All we're doing is we're simply comparing it to the points around it. All right. We're not talking about, we're not talking about a minimum or a maximum of the entire function necessarily. We're just talking about relative max and min. We're just comparing it to the points that are right around it. So if we had, just throw another one up here. Okay. So relative maximum, that's the point. It's simply just the point where the function is higher than the points immediately around it. So like here, for instance, we can clearly see that this point here is at the top of the local hill. It's higher than all the points around it. So this would be a relative max. And then say down here, relative minimum is the point where the function is lower than the points immediately around it. So if you look at everything around it here, look from here to here, if you look at the area immediately around it, this is our obvious low point here. So this would be our relative minimum. This would be the local valley. All right, so we have a hill. We would have another one here, another relative max, or if you want to think of it like a hill, and then relative min. We're down here in, if you want to think of this like the valley, and then, let's say we kept going off here. Looks like we're about getting to another low point. So this could be another relative min, or again, if you think of it like in terms of hills and valleys, another valley. So I think it's a lot easier just to think of it. It's just much more simple to think of it as you're comparing it to what's immediately around it. This point is clearly higher than everything around it. It tops out here, just like this point is lower than everything around it. We bottom out right here. Then we top out again. We have another hill. And then, assuming that this kept going, if this went like this, well, we bottom out again. Looks like we have another valley. So relative max and relative min. And if you wanted to think of it in different terms, you could always think of it too as if we go from increasing to decreasing, that's equivalent to where we would have a max. Like here, we are increasing, because we know how to find that. We know how to visually pick that out now. We go from increasing, and then we top out at a relative max, and then we go to decreasing. So where the behavior changes from increasing to decreasing, you would find a relative max. And then on the flip side, if you go from decreasing and then you change behavior and go to increasing, there you would find a minimum. So here we go again, continue this. We're decreasing, function is decreasing. All right, we bottom out. So this is going to be our relative min, because right after that, then we start increasing. So you can think about it in these terms too. Going from increasing to decreasing, you'll have a relative max, and decreasing, increasing, a relative min. So where behavior is changing. Let's try one quick example. Okay. All right, so what are we thinking with this one? If we said, well, let's say this here is 2, and then this will be 4. Okay, we'll need those. Something that kind of gives it away a little bit. So if we're looking for what do we have at when x is 2? Right? What do we have we're looking for? Relative maximum and a relative minimum. What do we have there at when x is 2? Okay. Well, looks like we have a hill. It's certainly higher than the points immediately around it. And we're going from increasing to decreasing. So we just said when we have a change of behavior like that, that is a telltale that we have a relative max. So we would say the relative max there is at, and here we would do it as an actual xy point. So if we say this is 2 as well. So we would say 2, 2, we have a relative max. And here we're decreasing, and then it starts increasing again. So when our behavior changes like so, all right, so we can see here, we have, this is our hill to now we're in our valley. So we have a low point here, lower than all the other points around it. So this must be a relative minimum of this function, which will be at, we'll say this is -2. So this would be 4, -2. We have a relative minimum. Another characteristic that we can identify by looking at a function and its graph is whether it is even or odd. Even and odd functions. So given a function, given a function f of x, the first thing that we want to do is replace, in order to determine if it's an even or odd function. First thing we always want to do is replace the f of x with f of -x. Place, So given of f of x, whatever it may be, for each x, we're replacing it with negative x. So that's the first thing we want to do, regardless. And now, if when we do that, okay, we replace it with f of negative x, and then we solve and simplify it. So if we do that, we replace it with f of negative x and we simplify it. If it comes out and equals f of x, if it equals the original equation, then we would say that this is an even function. We replace f of x with f of negative x, we simplify it. If that equates to negative f of x, that is an odd function. So if it equals, so again, first thing, we always do this first and foremost. If it comes out to equal the original equation, it's even. If it equals negative f of x, then it's odd. And it could be neither as well. That is a possibility too. But let's go right into an example so we can see this for us. Okay. So if we're given the function f of x is equal to x cubed minus x. All right, first thing we do, let's plug in f of negative x. So we do that, we end up with negative x cubed and then minus a negative x. So each x has been replaced with negative x. All right, so what happens here? So f of negative x, this equals, so negative x cubed, if we take negative x times negative x, if we square it, that becomes a positive. But when we multiply it out again, then it remains odd. And if you remember, if you have an odd number in the exponent, then it'll stay with the negative. If it's an even exponent, then you'll end up with a positive. So this will stay a negative x cubed, and then minus a negative x would become, we have double negatives, so that'll be plus x. So when we do that, when we plug in f of negative x and we simplify it, we end up with negative x cubed plus x. All right, so let's compare it. Does that equal the original f of x? And it does not. So we would say, so we know that it is not even. All right, it doesn't equal the original, so we know it's not even. But now let's try, does it equal negative f of x? So if we take negative, so we know this is f of negative x, so let's figure out what negative f of x is. And all that's saying is take your f of x, all right, f of x, which the original f of x is x cubed minus x, and all we're doing is, we'll put that in parentheses, we're just saying the whole thing is negative. All right, so make sure you know the difference between what we did with f of negative x and negative f of x. For negative f of x, we're saying the entirety of f of x is negative. So what we're going to have to do is distribute this negative. All right, so we distribute the negative times the x cubed, so we end up with negative x cubed, and then negative times a negative will get plus x. So now look what we did here. Negative f of x is equal to negative x cubed plus x, which happens to be what we found for f of negative x. And if we look up here, we said if f of negative x is equal to negative f of x, then it is an odd function. So that is our answer for this first one. F of x equals x cubed minus x is an odd function. So let's run through this process again. Let's do another example. We'll do f of x is equal to 2x squared plus x to the fourth. Right, same process again to start out. Do f of negative x. So when we put that in, we end up with, we have 2, and then we have negative x squared plus negative x to the fourth. So negative x squared, that'll become positive. Negative times a negative will get us positive. So we end up with x squared times 2x. So that'll just be 2x squared. And then we have negative x to the fourth. Since we have an even power, we have an even number in the exponent, this will become a positive. So we'd have plus x to the fourth. So let's compare. Does our f of negative x, does that equal the original f of x? And it looks like it does. So when f of negative x is equal to the original f of x, then we say it is an even function. So that is our answer for that one. And we will try one last one. So f of x is going to be equal to x to the fourth minus x to the third. All right, we know what we have to do first. Plug in f of negative x. Same thing each time. So we have negative x to the fourth minus negative x to the third. All right, so simplify that. So negative x to the fourth. Right, we have an even number in the exponent, so that's going to become positive. So we end up with x to the fourth. And then here we have negative x taken to the third power, so that's odd. So that's going to remain negative, but we're subtracting a negative, so that'll become plus x to the third. So we have x to the fourth plus x to the third. And does that equal the original f of x? It does not. We switch signs there, so that does not work. So it's not even. All right, well, let's try and see if it's odd then. So we need to figure out what negative f of x is. So again, throw the negative out front and then put it in parentheses. F of x was x to the fourth minus x to the third. So negative f of x is equal to, so we distribute the negative, we end up with negative x to the fourth, and we have a double negative, so that'll be plus x to the third. So negative x fourth plus x to the third. So does this equal this? Close, but not quite. We got a negative on the x to the fourth. So that tells us it is not odd either. So if it's not even and it's not odd, then we would say that it is neither. So that is our final answer for that one. And we can also determine even and odd from a graph as well, without having to do necessarily having to do the f of negative x. We can determine it from a graph. And the graph of an even function, we'll start there. Start with an even function first. The graph of an even function is symmetric with respect to the y-axis. So let me show you what we mean by that. And we're going to graph. This is going to be a graph of x squared. It's x squared, that is an even function. So we are going to graph what x squared looks like, roughly what it looks like. Okay, so this is our x squared here, function x squared. All right, so what we mean by symmetry about the y-axis is if you were to plot some points here, like if we did a table of values, we'd have 3. 3 squared is 9, so we'd have 3, 9. But then what would we also have? We also have negative 3. Just like if we were to go up to, if we were to plug in 5, we would have 5, 25 as a point. And then we'd also have negative 5, 25 as a point. So when it's symmetric about the y-axis, like this for an even function, for each xy point, we're going to have a negative x y point. This tells us we have symmetry about the y-axis, which we can see here. I mean, they mirror each other. We have a point here, we have a point here, we have a point here, we have a point here. It's going to be symmetric here about the y-axis wherever we go on x squared. And when that is the case, let me write it in here. So this is even, and we have y-axis symmetry. So that's how we can tell, just purely based off of a graph. If it has y-axis symmetry, it's an even function. And now let's compare that to, we'll show an odd function. And the graph of an odd function, as you'll see, is symmetric with respect to the origin. Okay, so now show an odd function, and I'm going to use f of x equals x cubed. That is an odd function, and that one's an easy one to remember how to draw. And when I say it's symmetric with respect to the origin, I'm talking about, so we have odd is origin, symmetry, origin meaning 0.00. So if we draw x cubed, so that one looks something like something like that. Close. So this is x cubed. And if we were to make a table of values, we would see our similar symmetry going on here. We'd end up with -3, which would get us to -27, and then -2 would get us to -8, -1, -1, 0, 0, and we'd end up with, would be flip-flopping. We'd go from a double negative to a double positive, because what we'd see with odd symmetry is for each xy point, it has an equivalent negative x, negative y point. Because we're dealing with this quadrant here and this quadrant here. So we go from this quadrant where they're both positive, to this quadrant where we have a double negative. So that's how we know that we have symmetry about the origin here. If we plotted a point here and a point here, we'd see we are indeed symmetric. So odd functions, symmetry about the origin, aka the point 0, 0. Even functions, symmetry about the y-axis. It mirrors itself over the y-axis. So that's how you can tell even and odd, just based off of the graph, without doing what we did before when we were doing it with equations. All right, so that's going to do it for this lesson. Hopefully it was helpful, and thank you for watching as always. Be sure to check out the channel for more algebra lessons.